Hey everyone, so back to our branch example here because I want to show you a technique that can simplify the problem solving that we looked at so far. So again, what we did is we created a connectivity for each object that we want to connect with lines. Then we scatter on them because those will be the connection points. I resetted the color because I don't need it. And then what we used here is the near points function to find points in a certain distance. And then because we can run over these points in an array, we can filter out, so to say, all the points that have not the same class attribute. In other words, we only connect points that are not on the same object. So I think this workflow makes sense, but there's actually an easier way of doing this. And this is not only applicable to arrays, otherwise I would have put it in the last video, but also to, for example, minpos. And that is groups in vex functions. So for example, when we look at the near points function, we've seen, okay, you can add the point vector, which is p, or the attribute p, and then a max list, and then a max point, so that you can limit how many points will be given back in the array that this returns. But in the next line, we have something we haven't talked about yet, and that is the point group. And this seems like, okay, well, a normal group, just like we know it, but it's actually pretty powerful because what we did here in our for loop, we can actually do already up here in our original function. We can filter for certain things. So let's try this actually. Let's go from scratch, copy this, and let's delete all this for now. And what I want to show you is that we only have to add a single element to our already existing one. So the point group, after that comes the point and the max list, just like up here. So it's really just one additional element to it. And this looks like this. We wanted to filter for everything that doesn't have the same class. And in a blast or something, we would write it like this: add class unequal to our current class. So let's say 1 or something. And this actually would work. It would find every point that does not have 1 as a class. So let's quickly try that. So we don't need that check here anymore. We only need this polyline, because in this group that we have saved here, there only will be those points that are not in class 1. So that this will look like that. That, as you can see, it's not what we want, but you can see this branch here is ignored. So, but that's not what we wanted. We didn't want to ignore a single branch. We wanted to ignore everything that does not have the same class as our own branch. So what we have to add here somehow is our own class. So it's not like this. That doesn't work. You have to actually put in a number by adding it to the whole thing after the unequal. And the attribute, of course, is called class. So this looks a bit weird, but what's happening here is it's checking if the class in the points that we're looking for is unequal to, and then the number of my current class that I'm reading out here. So it's not part of the checking. This will return a number basically. Now, unfortunately, if we check this, it will throw an error. And this error is you can't connect a string with a string plus a float. What does that mean? So this doesn't work. You can't add, and I think we talked about this when we talked about data types. You cannot say hello plus 5. That doesn't make sense. That's not a logical thing to do. But of course, what you can do is you can turn the 5 into a string, and then of course the result would be hello 5. That makes sense because both have the same data type. So what we have to do here is this number that comes out of the class, which is, by the way, an integer, just to be clean, and we want to turn it into a string. And we can do this with a really weird function called I2A. Don't ask me why they called it like that, but I2A stands for integer 2, and now actually it would be string. Let's quickly search for that. Let's see what side effects has to say in their defense, and not much. It's still just called I2A, and it converts an integer to a string. And as you can see down here, there are a couple of other functions to do the same. Don't ask me why they didn't call it I2S. I don't know. Maybe someone else knows it, but that's a very important little function to turn a number into a string. So now, as you can see, all of a sudden it works because now, like we had before, the points will only find those points that do not have the same class, and we do not have to filter for it afterwards. So technically that means we also don't necessarily need the for each loop, because all we care about is the first one that we will find. So we could actually add here the endpoints and just take out the first one of them. So 0. There you go. And as you can see, it works the same. Well, actually not completely. Oh yeah, as we can see, we still have a lot of lines, and that's my fault. I forgot about this. The problem with this is if there is nothing in endpoints, then this should not happen. Currently, even if we find something or not, we will create a line. And this is why all the points are connected to the center of the world. So we still need to do one check, and that is, and actually, by the way, we don't need this debugging anymore. We have to check, okay, if the number of points in endpoints, which we can check with len, not length this time, because we're not calculating the length of a vector. We're calculating the elements of an array. So how many points are in this array? And the name of the array is endpoints. If this is higher than 0, so if we actually found something, only then will we create a new line. And this is actually what we wanted. And now we have it as before. So, I mean, you decide if you prefer this workflow. Let's get rid of the debug line to compare it properly. Or if you prefer this workflow, it's a bit shorter, but at least you should know that this is possible. You can actually already filter in your function before you even get points back, so you don't have to do it manually yourself. Now in this case, okay, you could argue, well, both comes out the same. It's just a different way of writing it, right? And you're right. But there is actually a case as an example where this makes sense. And that is, if we think about what we just did, is we read out here the position of the point that we found, and the whole goal of this is to find a position on the surface of our branches, right? So if we wanted to connect this point here with the other branch, we actually just wanted to have the closest position. We don't really care if there are points or not. We just use this as a helper by scattering points onto it. And what I'm trying to explain here is we could have used the minpos function, right? Why didn't we use the minpos function from the beginning? So let's try that. We scatter on our branches again, and this time we don't need that many points. And this time these points will only be the start position. And we want to find the closest point on the other branches by using minpos. So let's do this. We create an empty point wrangle, and since we want to look for the closest position on the surface, at this point here we don't have a geometry anymore. We have points. So let's check where we have our geometry there. So this will be our second input. And this is something we've already done a couple of times at this point. We want, for the current position, find the closest point on the surface of the second input. So let's do this. We call this P2, and we check for the minpos on the second input based on our current position. Okay, so now on every point we have a position saved called P2. So for every point now we calculate point 2, which is the closest position on the surface of these bunch of branches, right? So let's try to visualize this in form of a curve. So we create a new curve with @prim, and it's a polyline. And the polyline needs two inputs, the starting point and the end point. We have the starting point, which is our current point, but we don't have an end point yet because we're not actually looking for another point, we're looking for another position. So once we found this position, we have to actually create a point at this position. So let's do an add point to the current geometry with the position P2. And this new point will be our second point of our line. And what happens? Seems like nothing happens. Let's double check if actually we did something. Yes, we created 91 primitives, so curves, coming from 91 points. So we did everything right. But the primitives right now are incredibly small because what we found with the minpos, you guessed it, the closest point we find on the branches relative to these points will always be the point itself. Because what we can't do with the minpos is we can't filter for something. And this is why I showed you that you can work with arrays so that you can filter something. Now wait, we just learned we can actually filter in most functions. So let's see if the minpos function can do the same. And there it is. So far we worked with just the point vector, and we can have a maxdist if we want. But here on the fourth line, we see we also have a primitive group here. Oh, that's brilliant. So let's try that. So we say we only want to get the minimum position for everything that does not have the same class as, so unequal, than mine. And mine was I2A because we have to convert it to a string. Yes, right, the class attribute. And unfortunately, this is not working when we look through it. And the reason is that actually on the second input, there is no class attribute. So this filter here, of course, applies to the second input, but there is no class attribute. Oh, here, our connectivity, we forgot to connect it, but it's still not working. Why? Well, be careful. When you use a group, this is a primitive group because it looks for a position on a face. So it's not looking for points, it's looking for primitives. And this is where the problem lies. This connectivity here creates the class attribute on the points. So we could promote this, or we just create a second one that we set to primitive. And now you can see all of a sudden it works. Yes, it's a bit more work. That's why it's in the advanced version. But as you can see, the cool thing about this is now it doesn't find anymore just the closest point on the surface, but actually the closest position on the surface. And this is pretty cool. And you could even, if you want, as we've seen with a minpos, add a maxdist to it if you want to limit it. So if you don't want it to find, super far away stuff. So let's add another parameter, the maxdist filter, and then we can define how far this thing looks. So as you can see, this is an even more elegant way of doing the whole thing because we don't look for another point. We don't use arrays. We do what we want to do. We find the minpos, but only under certain circumstances by, for example, only finding the closest point to an object that has a class that is unlike this class that we have. So in other words, we only find the closest position on the surface of an object that is not the same object the point is on. So this is how you can use point groups. And the cool thing is you can use this for a lot of functions. So the minpos has it, the nearpoints has it, and you will see that other functions that we haven't talked about yet, for example, pcone, which will come in a later video, also has that. Just be careful. Sometimes it's a point group, sometimes it's a primitive group, but you can use it to filter for certain rules. And you can imagine this is pretty powerful, as we can see here. So I hope this is helpful. Thanks very much and see you later. Cheers.